I think that's certainly considering those is important when you're thinking about planetary evolution. But if we're talking about planetary formation, I would exclusively look at the chondrites.
Hey, awesome. Let's give them a warm applause. And next up, we have Julie Inglis, who's going to be talking about a young triple system.
Hi, everyone. Can you hear me okay? Okay. So my name is Julie Inglis, and I'm a fourth-year graduate student at Caltech, working with Heather Knudsen. And in case anyone is keeping a running list of all of the grad students who are on the job market this fall, you might want to slot my name in there because I will also be joining them. But today I'm going to talk to you about the first project I worked on in my PhD and some work that's followed from that, which has been looking into the origins of Roxas 42b, which is a companion to a young binary star. Roxas 42 is located in Brilov, and what this allows us to do is determine the age of the system reasonably well, to about 3 plus or minus 2 million years. That in combination with the measured luminosity of the companion Roxas 42b has enabled us to put a mass of this object at about 10 Jupiter masses, so right at the planet brown dwarf mass regime. So this object orbits at about 180 OU away from a young stellar type binary, which has one star that is about 0.8 solar masses, and one that is about 0.3. So one of the questions that naturally arises from this, given the wide separation and the extreme mass ratio that this has with its host stars, is how did this object form? And being that it's relatively near the planetary mass regime, we ask the natural question of, did this object form in a protoplanetary disk? And if this object did form in a disk, the naturally arising question is, did it form more like a planet via something like core accretion, or did it form via a process that is known to produce binary brown dwarfs, disk instability? And if we, to first order, we can make very simple testable predictions about what these two different mechanisms would, the signatures that they would leave in the atmospheres of planets formed by them. Something that formed via core accretion, you would expect, given that it is embedded in the disk, it's accreting a lot of solids and might be accreting in various regions of the disk, could have a large range of possible atmospheric compositions, very different from that of its host star. Whereas a process like disk instability, which forms close and binary stars, which tend to look very similar, involves direct collapse of both the dust and the gas components of the disk, should produce something that looks very similar to its host star. So our goal was to test whether we could see how this companion formed by looking at the composition of its atmosphere. So to do this, we used both a combination of a medium resolution spectrum, that was first published by Brendan Bowler back in 2014, and also a high resolution near spec from Keck on the ground spectrum that was published by Marta Bryan a few years later. We did retrievals on both of these data sets using the code Petit Ratrans and tested a variety of different models in different chemistries and different cloud properties. And one of the most immediate things that we noticed during these retrievals is that we have some severe degeneracies in our PT profiles from clouds, particularly with our low resolution data. So the low resolution PT profile is shown on the far left here. And as you can see, the retrieved PT profile favors a very isothermal solution. In the middle, we show our PT profile from our retrievals only on our high resolution data. And we see that this conforms a lot better to what we would expect from theoretical predictions. I'm comparing it to a model from the Sonora model grid right there, based on the predicted log G and temperatures for this object. And the reason we think this is given to what levels of the atmosphere we are probing with these data sets. So the shaded gray regions here represent the layers of the atmosphere that are contributing to the flux that we are observing in these spectrum. So we see for our low resolution data, these dotted lines here cross the Sonora PT profile in the midst of the highest contribution to the flux. Whereas for our high resolution data, the bulk of our flux is emitted high above where these cloud condensation curves cross our PT profile. So we think that is just the unfortunate luck of truth of this object, that The clouds are significantly biasing our low resolution data for this, whereas our high resolution data is relatively agnostic to it. And we see this is true in our retrieved composition, where for our high resolution retrievals, we find our models are completely invariant of clouds, and we retrieve a very consistent composition for the atmosphere of this object of about a solar C to O ratio and a slightly subsolar metallicity, though our metallicity constraints are not the greatest. But this measurement in and of itself and compared to solar does not mean much. It's very important to place it into context by using the information that we can get from its host star. So to do that, we used a sniff spectrum of our unresolved binary and the Sphinx stellar model grid that was produced by Aisha Iyer to place constraints on the compositions of these host stars. So we modeled this as a two-component contribution to this unresolved spectrum and assumed that both of them would have the same composition, given that they are very close in binary. The projected separation as of the early measurements published by Adam Krauss back in 2014 was about 8 to 10 AU. I hit a button I should not have. Okay, great. Yeah, so the separation is about 8 AU, and studies in literature have shown that binaries at this separation tend to look very similar to each other. So doing this, we find, in fact, the composition of both the companion and the binary agree very well, so they're consistent with each other. And then after making these measurements, we now had to figure out how to interpret this. So from the first order simple predictions we made earlier about core accretion versus disk instability, we would expect from this measurement that this favors a formation via something like gravitational instability. But the picture turns out to be a little bit more complicated for things that form this far out. So we saw earlier that simple toy model that Karen Oberg made back in 2011, and we looked at how the composition of the gas and the dust varies as a function of location in the disk. So what we did, using some disk models run by Yayati Chachan, is look at how the relative amounts of dust versus gas accretion affect the final composition of something that forms this far out beyond the CO snow line. So once you are out beyond the CO snow line, almost all of the carbon and oxygen barriers have been removed from the gas phase of the disk onto the ice and to the solids. And what's left in the gas, maybe you have a bit of CO remaining, which gives you about a C to O ratio of your gas of about 1, but there is very minimal CO in this gas phase. So it's very hard for your gas to influence the composition of your atmosphere unless you are extremely low metallicity. So you've accreted very little relative solids. So what this plot shows here is our retrieved atmospheric metallicity between these two lines. And then this is the log fraction of carbon in the gas and the atmospheric metallicity of the final planet that you formed, which is a proxy for the solids that you have created. And what this plot shows is that in most scenarios, it is extremely hard when forming outside of the CO line via a method like core accretion to look like anything other than your host star. So this method does not seem to be as diagnostic for probing the formation mechanisms of these objects at this far of a distance. So all we really know for sure about this object is that it looks very similar to its host star and maybe could have formed in a disk, given that it looks very similar. So we have to turn to other metrics to try to probe the origins of these far out objects. And one of the ways that we can do that is by looking at the host binary, which I mentioned earlier. And having a binary host star can dramatically influence companion formation mechanisms. So if you're forming in a disk, you typically would expect that the forming object, the forming companion or planet, would have an orbit that roughly resembles the plane of that disk if it formed within that disk. However, binaries, as a function of their separation, can drastically affect the shape, the size, and how long the disks exist. So these companions that we are observing around these binary stars, this adds an extra level of complication into interpreting their orbits. And it can be a very strong function. The disk morphology can be a very strong function of the orbit of the binary. So close-in binaries, ones that are within a few day orbit of each other, don't really affect the structure of their disk that much. You can have a very stable circumbinary disk in that case. But the more intermediate ones, the ones that are out at, say, 10 AU, as this binary appears to be, can have a much more profound effect on the disk. And if you, during surveys of these disks, you can even find that the orientation relative to the orbit of the binary can go from being edge on to being completely polar, like in this image, the orbit of the binary is like this, and the disk is completely polar to the orbit of the binary. So while we might want to use the orbit of the binary to see if we can measure whether or not this object formed into a disk, we first need to understand what the orbit of the binary itself looks like and what the orbit of the planet is relative to it. And they've seen for studies of planets, circumbinary planets that are transiting, that they don't tend to have random aligned orbits with their host stars. They tend to be more around the plane of the binary's orbit or closer to 90 degrees, like I'm showing in this, like in this image right here. So what I want to do is measure the orbit of this planet around the binary, this companion, sorry, and see if this can give us any extra information about how this system formed. So we do that using about 15 years of monitoring with Keck, starting way back in the early 2000s. And what we find is that coincidentally, the system, this binary, is very edge on, which is helpful for a couple of reasons. So having a companion way out at 180 AU orbiting, you're not going to see much motion. So I would like to get my PhD before I turn about 100. So having a binary that we were able to track the motion of, and also very easily and quickly tell us that this planet is not aligned with its binary. So this is an image basically showing where the planet is with respect to the binary. So you have an edge-on binary like this, and then you have the planet sitting out way out here. So there's very, very small chance that that planet is on an orbit that aligns with this binary. So that in itself tells us something interesting about this system. But unfortunately, we're going to have to wait to know a bit more about the orbit of the planet itself, companion itself. But yeah, so what this has been able to tell us is that the companion, Roxas 42Bb, is very similar in chemical composition to its host star, but this is degenerate with between two different possible formation mechanisms within the disk. And that it is on a very misaligned orbit with its primary binary, but this might not be inconsistent with formation in a disk because the disks around binary stars can be warped quite substantially, and dynamical interactions between the binaries and the disk, and also the binaries and the companions following the dissipation of the disk, could explain why it is on this orbit that is not aligned. So there's a lot more work that needs to be done, I think, to understand these systems. And I think looking at multiple of these systems is going to be pretty important to really begin to understand how these systems that are orbiting binaries are different from ones that are orbiting single stars, and also to learn more about their origins. And with that, I'm going to show a picture of my own little buddy system. And I won't take any questions.
Okay.
Yeah, so this object is right in the temperature range where FPH condenses into here. And what my student Melanie Rollins has shown is that if you don't include non-uniform FPH bias, various aspects of your retrieval could be considered non-uniform in either your low res or high res.
Yeah, so we were typically assuming chemical equilibrium for these calculations. So we were using chemical equilibrium codes that accounted for condensation, but I mean, depending on how well they account for that. We didn't do free retrievals because they just turned up kind of nonsense results.
Yeah, so I have a question about so the inner binary has the separation. And so I would expect it to expect this how where the object is today. So we talk a little bit about what scaling the perspective of this with her.
Yeah, so my understanding is essentially that it's basically a variation of Kozai interaction. So if you have an eccentric binary, like this binary from our orbital fits has been shown to be eccentric, you can essentially tilt the entire disk relative to the plane of the binary's orbit to a very extreme inclination. And that's the process that would more be responsible for having a pretty drastic different orbit for the binary. As to whether it would affect the chemistry or the disk or anything like that, I think that's a pretty relatively unknown answer. So, yeah.
One more question while we get speakers. Oh. Okay. Those, multiple